In this video, we will be developing the formula that we can use to solve vertical motion problems. When we were studying derivatives, we found that the position function is called s of t. The velocity function is called v of t, and you can get that velocity function by taking the derivative of the position function. And the acceleration function is called a of t, and you can get that by taking the derivative of the velocity function or by taking the second derivative of the position function. So whenever we're doing vertical motion problems, we need to remember the order s of t, which is our position function, and then v of t, which is our velocity function, and then a of t, which is acceleration. So take the derivative of s of t, that gives us velocity, v of t. Take the derivative of velocity, and that gives us a of t, which is acceleration. So we'll be using integration. We'll start with the acceleration function, and we're going to go backwards. So we will use integration to get the velocity function, and the statement will be the integral of a of t. Integral of a of t gives us v of t, plus a constant, of course. And then we can use integration on the velocity function to get the position function. So we'll do an integral of our velocity to go back to our position, plus a constant. So let's develop this formula. We want to use integration to get the vertical motion formula, which is this formula. So we will get this at the end of our work. And we're given that acceleration is g. Now this is a constant. Usually g is 32 feet per second, but in some cases, some problems, if you're on the moon, you have a different acceleration due to gravity, or you may be dealing with meters per second. But either way, this is a number, so keep that in mind when we do our integration. But that's what we're going to start with. So we have a of t is equal to g. Now we know that we need to integrate acceleration to get back to velocity. So we're going to integrate both sides of this equation. We have the integral of a of t, and the variable on this is t, so we'll have to integrate with respect to t. And then the integral of g with respect to t. So basically all we did was integrate both sides. Right? And let's say this again. The integral of a of t is v of t. So when you integrate acceleration, you go back one step to your velocity function. So this is v of t. And we want, remember this is a number, so if we want, we can think of this as g times t to the 0 power. That'll help you remember, since we're integrating with respect to t, our variable is to the 0 power. So when we integrate, we increase the exponent by 1 and then divide by the new exponent. So I now have v of t is equal to gt to the first power plus a constant. Now we're going to use our initial condition. The notation for velocity at time 0 is v sub 0. So, and again, this is a constant as well. Velocity, you may think of it as your speed limit. So our velocity, it would be like 55 miles per hour or whatever. That would be what v is, v sub 0 at your time 0. So that's also a constant. So now let's write this in our initial condition format. Our initial condition is that the velocity at time 0 is v sub 0, this constant. So now we can take our velocity function that we got when we integrated. Remember that this means t is 0 right here. And when t is 0, v of t is this number, v sub 0. So we're going to plug those in. In place of v of t, I'm going to use v sub 0 equals g times t is 0 plus my c. Well, this product is 0, so v sub 0 equals 0 plus c, which means that c equals v sub 0. So now we can write the particular solution. This was just the general solution. Our particular solution for velocity, v of t equals g times t plus our constant, which is v sub 0. Now our problem asked us to get the formula for position. What we have now is our velocity. We started with acceleration. We now have velocity. We have to integrate one more time. So we're going to do that process again on this equation. So we want to integrate both sides with respect to t. Integral v of t with respect to t is equal to the integral of gt plus v sub 0 with respect to t. Now when we go back from velocity, integrate velocity, we get our position function, which we call s of t. Let's break this into two separate integrals. Remember, g is a number, so our variable t is to the first power. We want to increase that exponent by 1 and then divide by the new exponent. So we now have gt squared divided by 2 plus, and this also is a number. I'm going to write that integral in a step here. This is a number, v sub 0, and then we could think of this as t to the 0 power to help us remember that we increase that exponent by 1 and then divide by the new exponent. So s of t is, I'm going to write this as 1/2 gt squared, and the new exponent here is 1, so it's v sub 0 t, and then plus our arbitrary constant. Now the notation for position at time 0 is s sub 0, and this also is a number or a constant. For example, if you started 10 feet above ground level, then s sub 0 would be 10. So this is your position at time 0 where you start. So we'll use that in our initial condition. So we have s at time 0 is equal to s sub 0. So that means when t is 0, s of t is s sub 0. So now we can sub into our position function. This is our general solution. So we're going to sub these values into our general solution to get a particular solution. So in place of s of t, I'll write s sub 0 equals 1/2 g. In place of t, I want 0, and that's squared, plus v sub 0 times 0 again, and then plus our constant. So we want to solve for our constant. This term is 0 when we multiply. When we multiply here, this term is 0. So we see that s sub 0 equals our constant in this general solution. So now we can put in our value s sub 0 in place of c, and we have s of t equals 1/2 g t squared plus v sub 0 t plus s sub 0. And this is that formula that we were asked to develop.